So, welcome everyone for the last meeting of the semester, the fall semester, and it's clearly the winter is here to stay for a few months. This was a very eventful week in astrophysics. I just want to mention three important discoveries that were reported before we listen to Anna. One is a binary called LB that includes an object called LB1, 70 solar mass black hole with a B star companion. That is 8 solar masses was reported in Nature. You might suspect it must be wrong because of that. But there were other reasons. I mean, this is a very unusual system in the sense that it needs to be nearly face-on. The distance estimate is twice the Gaia estimate, and the star is 35 million years old, so it's a bit unusual, the system, but it's the first report that such a black hole exists, and of course it has implications for LIGO. Then there was just yesterday a report, again, I think in Nature, about a white dwarf that is accreting mass, most likely from a Jupiter mass companion from the planet, based on the composition of the material that falls in. So that's also exciting. First time that there is an indication for a planet, not planetesimals around the white dwarf. And finally, the Parker mission provided new data on the sun. And there are beautiful new movies that I recommend people to look at that came out again yesterday. So all of these things happened this week just to show how exciting astrophysics is. But to hear more about astrophysics, we have 4 presentations today. We just held an excellent colloquium by Yacine Ali-Haïmoud, who is not far from here at NYU, but we haven't seen you very often. We hope to see you more often. So Anna will talk about locating the dark matter subhalo with streamers. We will hear more about it. Then Tracy Slatyer will, again, we'll talk about dark matter. Is Tracy here? Yeah. Oh, okay. Good to see you. Tracy will, is even closer than NYU. She's at MIT. And many of you may remember her from the time that she was a student in the physics department working with dark field management. So now she's a professor at MIT, and she will talk about diversifying Milky Way satellite galaxies via dark matter self-interactions. Then we'll hear from Yacine about mapping the nanoHertz gravitational wave background with pulsar timing arrays. And finally, we'll hear from Maria Charisi, visiting us from Caltech, over there. And she will tell us about searching for supermassive black hole binaries. Anna.
Thanks, Avi. So, as we heard in truly excellent ITC colloquium today, there is abundant evidence for dark matter in the universe, and our standard cosmology predicts that there should be many small clumps of dark matter orbiting galaxies like the Milky Way that are completely devoid of any stars or gas. And so this is one of the crucial tests of the whole paradigm. But as you might expect, it is a hard test to perform because we want to detect objects that are low mass and completely dark. Luckily, we have globular clusters, and I'll show today how we can use them as a torchlight in our search. And for the purposes of this talk, we'll disregard all of the beautiful astrophysics going on in globular cluster, and we'll just think of them as point sources that, as they orbit around the galaxy, lose some stars. Due to two-body interactions, some stars manage to escape the globular cluster and form these 2 tidal tails. And since the stars are escaping with a very low velocity, stars that are escaping the cluster are on very similar orbits to the main progenitor. So the resulting stellar stream is somewhat thin and kinematically cold. And this is important because it can serve then as a sensitive tracer of all of this space or environment that it has been formed in. So for example, if we look into the model of a stellar stream formed in a smooth galaxy, such as one predicted in, for example, the warm dark matter cosmology, we get something that looks very regular, one-dimensional structure in the sky. However, if we take the same orbit and put the globular cluster in a dark matter halo that has a lot of substructure, such as predicted in a cold dark matter case, the resulting stream has a lot more features. So there are variations in width, density. There are some stars that are even ejected from this main track, and there are these gaps in streams. So this is our observable. We wanted to perform this test. We know there are streams in the Milky Way. We see disrupting globular clusters, and we just want to check whether they look like this or whether they have any signatures that we expect from these perturbations from low-mass dark matter subhalos. And this is a hard test to make because there's only so many globular cluster stars, and it's hard to pick them out from the rest of the Milky Way. However, thanks to Gaia, we can more efficiently select stars that used to belong to a globular cluster because they all move in the same direction. So this work came out just a week after the second data release from the Gaia mission, where Adrian Price-Whelan and I looked into one of the known streams called the GD1 stellar stream, and just selected the highly likely members of this stream. And what we saw was that indeed, like, most of the stream looks kind of regular, but there are two very prominent gaps. And when we created a model of the stream in a smooth galaxy, we could account for one of the gaps by saying that this is the place where the progenitor used to be, but then leaves this other gap and the structure that kind of comes out of it unaccounted for. So we thought, well, this would be exciting if it actually pinpoints the location where the stream encountered some unknown object, like possibly a dark matter subhalo. So we went ahead and added one additional component to our model of the stream in a smooth galaxy that encountered a low-mass object. And what happens then, some stars, like close to this impact location, receive velocity kicks. And then they are extracted out of the stream so that there's a gap that forms, and also some stars are extended out of the mainstream. And so this is in kind of galactic Cartesian coordinates. However, if we project this model as if it was observed from the Earth, we get something that looks like this. So on top, I'm showing the observed GD1 stream, and on the bottom, I'm showing a model that you just saw form. So you can see that qualitatively, this encounter scenario accounts for many of the features that we see in the data. We have the gap that is somewhat overdense, but not completely empty. We have stars extracted out from the stream at a kind of roughly correct distance from the stream and roughly correct extent. And what was very exciting about this model is that we require a mass of something like a few million solar masses to get this feature. When we explored the parameter space a little bit further, we put some constraints on what the mass and the size of this object should have been. So here are our limits in gray. And compared to some of the known objects in the Milky Way, we have dwarf galaxies as squares, globular clusters as triangles, and molecular clouds as circles. And so you can see that there is some overlap over here. We can probably rule out the molecular clouds. The lambda CDM subhalos occupy this region over here, and the dashed lines are showing the 1, 2, and 3 sigma scatter from the mass concentration relation. So there is a little bit of overlap here, but it looks like we are preferring much more compact objects than what is naively expected in lambda CDM. And taken at face value, we might think like, okay, this is most likely a globular cluster who's done it. However, again, thanks to the Gaia mission, we now also know the orbits of basically all of the globular clusters and most of the dwarf galaxies in the Milky Way. So we can just integrate them back in time and see whether they cross the paths with the GD1 stellar stream. And when we do this exercise, we can basically rule out all of these objects because they don't come close to produce this effect. So this kind of leaves us with a barren scenario, but we do have a few options. So it could be that this globular cluster that we haven't seen yet could produce this feature. It could be an unusual dark matter subhalo. You'll notice that these are sort of like the limits extend towards more compact objects. So technically, it could be a supermassive black hole if we could figure out a reason why it would be orbiting the Milky Way halo. So what we'd really want to do is predict where this object should be today and go look for it with some other means. So I have taken all of my models that occupy this region and projected where they should be on the sky today and got this. So not quite the localization we were looking for over here, but we could then make predictions for what to observe next, how to constrain it. So if I color code all of these models by the relative velocity between the spur, that upper part of the stream, and the main body of the stream, we see there are like some bigger trends. And the color coding goes from -5 to 5 kilometers a second. So this, gives us like a next agenda item. So we want to look at what are the existing radial velocity measurements in this stream. So they're shown here in blue, and you'll see that they are mostly on the main body of stream. And what we are looking for is the velocity difference between this upper part and the lower part. Here's the radial velocity difference with respect to the expected orbital trend for the overall stream. And so you'll also see the error bars on the old data are somewhat large, and the expected range that I was showing before was plus or minus 5 kilometers a second is shaded in gray. But luckily for us, the CFA maintains probably the only instrument that we could make this experiment on, and that is the hectoshell spectrograph on the MMT. So we went ahead and observed 8 fields in the stream, shown here on the main stream in orange and in dark orange in the spur. And these are the radial velocities average per field that we get. So when we zoom in, we see that there's basically no radial velocity difference between the main body of the GD1 stream and the stars that look like they are kind of extended out of the stream. So this then, if we go back to our sky localization map, we can then, instead of just plotting all of the models, just constrain it to those that have relative radial velocity between plus or minus 1 kilometer a second. So when we do that, we get this. So maybe not quite like LIGO localization, but still look like we do have some information on where the object should be at the present. So I thought this was very exciting because it opens up really a new way of how we study these streams and study substructure within the Milky Way halo. But what was curious about this is that this kind of looks like a great circle. And I thought, like, well, maybe this could be something that is already related to something that we know of in the Milky Way halo. And one of the prominent features is the tidally disrupting Sagittarius dwarf galaxy. And Marian Diericks, a couple of years ago, with Avi Loeb, created a model of such disruption that predicts star particles to be here and dark matter particles to be here. So I think this is kind of exciting, tentative relation that the perturber of GD1 might have really originated within the Sagittarius. And I'll take your questions from here. Thanks.
It's very exciting. So it means that you may have detected dark matter from Sagittarius rather than from the Milky Way.
Yeah, it still needs to be a compact object, what we are finding. But yeah, that's, I think this is, like one of the questions before was whether there are any dark matter subhalos so close in the inner parts of the Milky Way. So the newer simulations that include disruption of subhalos through baryonic disk were saying that in this region that GD1 is orbiting, there should be very few. But if they came together with Sagittarius, those encounter rates would need to be revisited. So I think that's kind of an exciting avenue. Yeah.
Yeah, so I know people have talked about widening stream from chaotic orbital dynamics.
Mm-hmm.
So is there another possibility to create this spur without a perturber, or has that been explored?
It hasn't been explored. Yeah, so it's a very new result. So everything is, out there. My sense is that those chaotic widenings are kind of have a more global effect on the whole stream. So this seems like a very kind of delicate feature, but yeah, I think it's an avenue that should be explored more. Yeah.
It seems like one of the aspects of this, as you were saying, is that if you work through this source in detail, you're sort of defining a method that you can apply to other gaps or features. And I wondered, as we kind of looked at that 3D version of the encounter and then its projection into this spur on the sky, is this kind of a worst-case scenario projection in the sense that from some angles you saw a much clearer gap? And does that mean that there are other streams that one could possibly do this on with sort of bigger features just by sort of chance of alignment? Or?
Yeah, that's a good question. So yeah, I might say that like if you were seeing this and it's not just like a chance alignment, it's also a time effect. You can see like that those loop or ring of stars kind of precesses around the orbit of the stream. So yeah, there's.
It sort of fills in over time.
Yeah,
okay.
and even just in GD1, like there is this other gap over here, and maybe another one at a different location. So yeah, it could be that with more detailed observations, we might see even lower surface brightness features that could be kind of mapped to these sort of origins. But yeah.
So about warm dark matter, lambda stream you cannot rule out, but can you completely rule out warm dark matter?
Well, I think if we have a mass constraint on this to be, well, I guess maybe some people know, like 10 to the 6 would be like 20-ish keV or so, I think. So yeah, I think it's in this regime where it might rule out many of the warm dark matter models, but I think we first need to actually show that it is a clump of dark matter and not something baryonic. Yeah, but that's why it's kind of motivating to do it. Yeah, because there's actual constraining power.
This is the smallest mass dark matter halo that we have detected.
Yeah, yeah.
Well, keep up with the excellent work.
Thanks, sorry.
Is there support? Okay, thanks very much for the invitation. I'm very pleased to have come all the way from MIT to talk to you about this. So I want to talk about a somewhat related topic, but from a more theoretical standpoint. Most of what I'm going to show you is about simulations. This is a paper based on work that was led by my PhD student, Yacine Ali-Haïmoud, who's applying for postdoc jobs this year and is very good, together with Felix Kalhofer and Manoj Kapling-Hatt. And it's actually on a topic somewhat related to what we just heard about. So I am nominally a particle physicist at MIT, and as you've seen, classic collisionless cold dark matter models, if you assume the dark matter interacts only by gravity, then you have a prediction for how the subhalos of dark matter around the Milky Way should behave. However, and we can do detailed simulations where dark matter has no interactions other than gravity, But from a particle physics perspective, it's interesting to ask what are the possibilities that dark matter could have its own interactions with other dark matter particles beyond just gravity. Because it turns out that while the interactions of dark matter with the standard model are pretty constrained, the interactions of dark matter particles with other dark matter particles are much less constrained. You can have interaction cross-sections that are comparable to the strong nuclear force and that is not currently strongly excluded. There are limits from the bullet cluster, and there are limits from looking at dwarf galaxies of the Milky Way. However, much of the work to date looking at these observational signatures of dark matter self-interactions has really focused on the case where you're looking at some isolated subhalo sitting out in space, and you ask, if we turned on dark matter self-interactions, how would that change the properties of that structure? So what we wanted to do in this work, and there were a couple of other papers doing similar things that came out at the same time, is to understand if we took a subhalo of self-interacting dark matter and threw it into a larger halo, as is appropriate for a satellite galaxy, then what is the interplay between the gravitational forces of the larger halo and the self-interaction effects of the subhalo. Okay, so we're just trying to understand, like, what would the observable signatures of dark matter self-interactions look like in terms of the properties of satellite galaxies of the Milky Way. Okay, so let me just give you a little background. So if we want to estimate the effects of self-interaction, basically what turning on self-interaction does is allows heat conduction between different regions of a dark matter halo. Okay. When the interaction rate is large, you can essentially model the dark matter as, rather than a collisionless gas, as a thermally conducting, gravitating fluid. In order for the interaction rate to be large enough to significantly modify the dynamics, you need it to be true that on average each dark matter particle in the halo is going to interact an order 1 number of times during a dynamical time of the system. If only a tiny fraction of the dark matter particles are interacting, then you don't typically get observable effects. We can estimate what kind of cross-section you need for that. So the parameter here is that the dark matter scattering cross-section times its typical velocity times the number density of the dark matter times the dynamical time of the system should be equal to about 1. We can rewrite, now we don't know the number density of dark matter, what we measure is its mass density, so we can rewrite this in terms of a particle physics factor, which is the interaction cross-section divided by the mass, and the mass density of dark matter, the typical velocity, and the dynamical timescale of the system, which you could hope to get an estimate from looking at the astrophysics. So for a typical system within the Milky Way halo, if you take throw in sort of typical values for the density, for the expected density and velocity of the dark matter, and a timescale on the order of 1 billion years, then you find that the cross sections you would need to expect to see large effects are of the order of 1 centimeter squared per gram for the scattering cross section divided by the mass. If we convert that into particle physics units, that means that if you had sort of 100 MeV dark matter interacting at the same strength as the strong nuclear force, that's about this cross section. So it's actually, like, you need a pretty big ray to do this. If you have a cross-section like this, then what happens? So the standard history for self-interacting dark matter halos is that first, the heat transport, if you start out with, at early times, with a density peak, as you would have expected just from the gravitational interactions at the center of the halo, you turn on these self-interactions, and over time it evolves into a flat density core at the center of the halo. The central density drops off, the halo becomes less concentrated in its inner regions, and for this reason, dark matter self-interaction has been proposed as a way to explain why at least some dwarf galaxies seem to be less dense in their central regions than we might have expected. There are other possible ways to explain that as well, beyond self-interacting dark matter, but this was like one of the original motivations for thinking about self-interacting dark matter. Now, if you wait for long enough, however, that core is not stable. This is, these gravitating systems have negative heat capacity, so over time, outward heat transfer can result in a gravithermal core collapse, where what started out as this flat, low-density core collapses into a small, compact, high-density region. Whereas, that gravithermal core collapse in isolated halos, to see it happen requires a pretty large interaction cross-section. Generally, you need to wait for like roughly 100 times this T0 timescale, where the T0 timescale is the thing that I was setting equal to the dynamical timescale up here. It's like the timescale for an average dark matter particle to scatter once. So in an isolated halo, to get the core collapse, the average dark matter particle is scattering like order 100 times. Okay. So now what happens when instead of looking at a field halo, we throw this into a larger system? So yes, well, we just heard about this. The Milky Way contains many satellite galaxies, which are clumps of dark matter and stars. So in satellite galaxies, we have an interplay between the self-interaction effects within the satellites, changing its density profile, the gravitational interactions between the satellite and the main halo, and of course there could also be self-interactions between the dark matter in the satellite and the dark matter in the main halo. For what I'm going to show you, for the analysis that we did, we ignored this last effect. The reason was because we wanted to look at the interplay between the first two and separate out the effects of the third one. That can actually be physically natural because in a lot of these models, the self-interaction cross-section is highly velocity dependent, so it's enhanced at low velocities. The relative velocities of dark matter particles within the satellite are expected to be much smaller than the relative velocity between the satellite and the Milky Way halo. So you can naturally have a case where this effect is negligible, but you could also have models where it's not. But for the moment, I'm just going to be looking at these two. So it turns out that what happens in this case is that the effect of tidal stripping is basically to amplify whatever trend the halo is currently experiencing with respect to its concentration. So you have these sort of diverging evolutionary tracks when you put these effects together. Suppose on one hand that I start out with a halo that, maybe it started with a high concentration, it started with a high density, the self-interaction rate was pretty high, and it's already started to begin to core collapse. If this happens, then the effect of the gravitational stripping of particles from this halo by the larger halo is to remove the outskirts, and that actually increases the rate of core collapse, which had been studied at the beginning of this year. So rather than having to wait 100 times the T0 time scale, the core collapse proceeds much faster, the inner core becomes much more compact, much more dense, more quickly. On the other hand, if at the point that this satellite halo comes into the high density regions of the main halo, it's in the phase that I mentioned earlier, when it has a relatively low central density, it has a large central core. That means that it's extremely vulnerable to tidal disruption. Anna just said that in these models where you take into account the baryonic disk, you expect dark matter halos to be heavily disrupted as they come into the center. Well, this is even more true for self-interacting dark matter halos that are in their low density, large core size phase. So the effect of tidal stripping is to amplify what the halo was already doing. If it's already becoming smaller and more compact, this speeds up the process. If it's already in a low central density stage, then you get larger cores, even lower density, or complete destruction. And these plots are just showing examples of this. So this is the density of the halo at a particular distance from the center of the halo. Here we were simulating 10 to the 9 solar mass halos, so larger than the ones that Anna was talking about, at a distance of 150 parsecs from the center. This is the case where you start out with a pretty high concentration halo. In the field case, you see that the central density stays pretty flat. Eventually, at the end, at 100 times T0, the density starts to rise. That's the beginning of the core collapse. These are two examples for orbits of satellite halos. You see that the density, initially it starts to drop off, but then the core collapse starts noticeably earlier. The turnover at the end when it goes down is actually because the core collapse has proceeded to the point that now all the density of the core is inside this radius. So, so this is where there's a 150 parsec core, it drops off, and that's because the core is even smaller, 150 parsecs. This is the example for the low concentration case. On the other hand, the field galaxy, as density is falling over time as it cores out, you throw this into a main halo, and if the orbit goes in close enough, the satellite will just get completely disrupted. Okay, so this is another way to look at the same thing. That if we look at this is looking at the density slope at for different self-interaction cross-sections in field halos in the top panel. So this black line is what happens in CDM, where you don't have any self-interaction. We see that the density keeps rising towards the center. We turn on self-interactions, and the density flattens out towards the center. And this is the classic picture of self-interactions. They reduce the central density of halos. They give you this core. But once you allow these satellites to evolve, in a galaxy, these are just two examples of orbits, so with different periods. So I'll just look at one. So what you see happens is that if you start with a high concentration halo, which was already undergoing core collapse, at the time snapshot that this is taken as, the central densities of these self-interacting halos are even higher than you would expect them to be in CDM. They've just become more compact because of the stripping of the outskirts accelerates the core collapse. in these. However, if you throw in a low concentration halo, you see that the cores are now pretty huge. They're larger than they were in the previous case, and the overall central densities are very small. And in fact, this is after 10 gig years of evolution. In these cases, we couldn't actually run out to 10 gig years because by that time the subhalo was destroyed. Okay, so I'm going to wrap up. So this was just a preliminary study, just trying to understand what is the range of possibilities. We haven't done simulations that would allow us to say what is the distribution of these properties, which is what you would need to do a direct comparison to data. But there is observation, like very qualitatively, there is observational evidence that there's a pretty wide scatter in the properties of the dark matter halos of Milky Way dwarf satellites. And maybe Anna is telling us that even smaller subhalos that don't have stars may also, at least some of them may be more compact than we would have expected. So this is just kind of an illustrative plot where you show the range of density within the half-light radius as a function of half-light radius for a bunch of observed Milky Way satellite galaxies, and the red and blue points are examples from our simulations. The blue is a smaller self-interaction cross-section, the red is a larger one. As you dial up the self-interaction cross-section, this diversity gets stronger and stronger. So if something like this was happening, what you would expect to see is both a wide range of halo properties, but since it's an environmental effect, you would also expect the properties of those halos to correlate strongly with their orbits. So by looking at, because it's coming from a tidal stripping effect, you would expect to see associations between these properties and, for example, the period of the orbit, its pericenter and apocenter, and how close it comes to the disk. Yeah, so that's basically what I wanted to tell you in 10 minutes. So as I said, I'm not claiming this is evidence for self-interaction at the moment, but this is a potential way to look for observational signatures of self-interactions. And if you take one thing away, it's that when you think about possible signatures of self-interacting dark matter, for satellite galaxies, the tidal stripping effects are likely to be really important. This is not a small effect.
So Tracy,
Yep.
your analysis did not include the behavior of the baryons.
It did, that's right.
So, I mean, presumably these satellites nowadays, they don't have much mass in stars and so forth, but they used to. And so
Good.
the question is, could the baryons modify?
Yeah, absolutely. Yeah, so I can say a couple of things about this. Yeah, so the only level at which we included the baryons here is that we put in the potential of a baryonic disk. So, but we did not include the effects of the baryons on the structures of the halos. We did try, so in the evolution that I showed you, everything started out as an NFW profile, but we did try putting in an initially cored profile, which is what you might expect to happen if there were a lot of stars in these systems early on, and that perturbed the original dark matter density cusp at the center of the halo. That does push you somewhat more onto the low concentration trajectory, but the effects were actually not very large compared to the other effects that we observed. So yeah, I think it's a really interesting question. And as I said, this was a first pass analysis. There's clearly a lot more to be done, but yeah, that's would be my best guess.
Yeah. So Tracy, you talked about thermal conduction.
Yeah.
Self-interaction can also give viscosity. Isn't that important?
Good. Yeah. So right. I mean, so the way that we simulated, right. I mean, the way that we simulated this is just we simulated the self-interaction as an energy transfer. We didn't make the approximation of treating it like a fluid that has some heat conduction thing. We simulated the self-interactions directly. But so that was more just sort of my simplified explanation of what's going on. So yeah, I'm not sure.
You mean in an n-body code, you actually had each interaction with some transfer?
Yeah, that's right.
Probably it already includes the viscosity.
So I think I think what we've done includes the viscosity. I'm not sure how best, but you could think about other models where you explicitly separated out the heat conduction effects and the viscosity effects and looked at so I think our simulation includes them both, and separating them it's not obvious what would happen. But you could do something else where instead of modeling the individual interactions, you modeled it as a fluid with some heat conduction and some viscosity, and then tried changing the parameters.
In a classical collapsing star cluster, you undergo the same core collapse because
Yep.
the body effects give you the same as the
Yep.
self-interaction. But eventually that's halted by some sort of energy source that you start liberating from the center, either binary burning or something else. Would there actually be something in this case, or would you essentially undergo gravithermal collapse indefinitely?
Right. So that, I mean, it depends on the dark matter model. But in the cases that a lot of people think about, like if there's no dissipative channel, so like for example, if the dark matter has a dissipative option for the self interactions, it can radiate off something light, then I can imagine that. Then I can imagine that playing a role. But yeah, I think for a lot, the sort of simple self-interacting dark matter models that people think about, where there's just some contact interaction or some velocity-dependent interaction, the eventual outcome of the core collapse is you make a black hole. I mean, it just keeps going. Yes. So if yes. So if you have a big enough I suspect this is ruled out for other things, but yeah, if you had a large enough cross section that the core collapse happened like for all dark matter halos on prompt timescales, then you would expect pretty much every satellite to have a black hole at its center and not a lot of dark matter left. So that it seems like you must be able to set an exclusion from that. Yeah.
Any other questions? Oh, go ahead.
Okay.
When you have a very large cross section,
Yeah.
then this dark matter would behave like gas, right?
Yes.
You will not have
Because of the pressure of the gas.
Exactly like gas. My next question related to this: if you have from the particle physics point of view, you can have such large cross sections for low velocity dispersion, and when the relative velocity is large, then the cross section would be sufficiently small as to avoid the political
Yeah.
strains and things like that.
Yeah, yes, is the short answer. So usually, to get that kind of velocity dependence, what you usually require is that there's some kind of relatively light mediator in the system. But I mean, if we have like a 1 over v squared scaling in the cross section, which is not that hard to get, then the typical velocities, internal velocities in these dwarf galaxies are, of the order of 10 or 30 kilometers per second. In the bullet cluster, it's thousands of kilometers per second. So you basically have 2 orders of magnitude in velocity. A 1 over v squared scaling is 4 orders of magnitude. Well, I said 1 over v squared. 1 over v to the fourth is even stronger. Like if you have a massless mediator, it's 1 over v to the fourth. If you have a massive mediator, but it is still relatively light, then you can get like 1 over v or 1 over v squared behavior. And, but yeah, like, I mean, even if with just like a 1 over v scaling is probably enough, right? Like I have 10 centimeters squared per gram here. 1 over v scaling is a bullet cluster cross section of 0.1 centimeters squared per gram. That's not excluded. Like that's fine. So yeah, it's not that hard from a particle physics perspective to get. I mean, the question that you might ask is, okay, what if we go to like just slightly larger systems? And there have certainly been claims that by looking at systems with typical velocities around 100 kilometers per second, that turning on self-interactions makes them too spherical. But often those claims, once people have actually done simulations including baryons, those constraints have gone away because it turns out that once you include the baryons, it doesn't behave like you would naively expect.
Thanks, Tracy, again.
Where's the DVI? Oh, I see. Okay, it worked when we tried it before. Yes. Okay. All right, so I'm going to talk about something that's completely different than what I talked during the colloquium. This is work in collaboration with Cala Mingarelli at the CCA and Tristan Smith at Swarthmore University. Cala Mingarelli is the actual real pulsar timing expert in this collaboration of 3, and Tristan Smith and I are the cosmologists who are like, hey, let's do something else than CMB. So most of the talk will be some broad picture introduction. So let me start by the success story of the CMB. So in the 40s and 50s, there were already some estimates of the temperature of the cosmic microwave background. These estimates were all over the place, between 5 degrees and 50 degrees. And in 65, as you know, Penzias and Wilson detected the CMB serendipitously at 3 Kelvin, and they talked to their friends, Dickey, Peebles, Roland Wilkinson, who told them this is actually the cosmic microwave background. So this number, this single number, 3 Kelvin, already sets, the picture of how the universe, the thermal history of the universe, happened up until, which was quite unknown at the time. So the epoch of radiation domination, the matter domination, etc. It was also predicted that this CMB would be have a black body spectrum, and this was indeed confirmed by the COBE satellite, which measured not only this one number, but also the full frequency spectrum of the cosmic microwave background. And the fact that this spectrum is very close to a black body tells us that no crazy energy injection happened in the early universe. The COBE satellite also measured, beyond this, the first full sky map of the temperature of the cosmic microwave background. So that's one more piece of information. It's not only the frequency dependence, but also the angular dependence of the cosmic microwave background. And beyond this, WMAP and then Planck have measured also full sky maps, from which, as you know, we now have this high precision cosmological model with measurements of all the cosmological parameters within very small error bars. Okay, so we are now in the early days of gravitational wave astronomy and perhaps cosmology. So this Galileo telescope, you can think of LIGO. Did they? Okay, I didn't know the story behind it. And just like there's a very broad spectrum of electromagnetic waves, which all probe a variety of different phenomena, from radio to gamma rays, there's also a broad spectrum of gravitational waves. LIGO sits at the very high frequency regime, at the hundreds of hertz to kilohertz. As you have heard, Lisa is planned to be in the millihertz frequency regime. And pulsar timing arrays are probably what is going to be the next experiment that detects gravitational waves, according to people who work on this, in the nanoHertz gravitational wave regime. And I think Maria will tell us more about this. So this is a one-slide introduction to pulsar timing arrays. So what are pulsars? I don't know if you can see. I just took this from my... It would be better on the blackboard. So what are pulsars? For all we care about in this context is that pulsars are very regular emitters of electromagnetic waves, radio intensity. So the first plot shows you these illustrates these regular blips of radio frequencies. So what one does is, as a function of the pulse number, compute the time of arrival of these different pulses. You then fit some timing model, some smooth timing model, which accounts for the spin down of the pulsar. Maybe this pulsar is part of a binary or something. And once you remove this smooth timing model, what you're left is what is called a timing residual. And this is an actual plot of a timing residual of this pulsar from has been observed by the nanograv collaboration. And you see this pulsar has been observed over a decade. Okay, so you have these tiny residuals of microseconds or so. So now, what's the link with gravitational waves? This timing residual, you can show, if you have some gravitational wave background, will be proportional to the integral. So this is units of time, this is dimensionless, the transverse trace-free metric perturbation. So this is proportional to the integral between the pulsar and Earth of this gravitational wave. And then if you have two different pulsars, you can cross-correlate timing residuals from two different pulsars. And this will be proportional to the power spectrum of gravitational waves if you have a stochastic gravitational wave background. So this has a lot of similarities, though also some fundamental differences with interferometry. Okay, so with interferometers, you can correlate the voltages of different radio antennas, which then relate linearly to the stochastic electromagnetic field, which is the intensity of the light. All right, so now to relate to the story I was... pulsar timing arrays, as I said, people who work on this will tell you very confidently that in the next 10 years, they should detect the stochastic gravitational wave background. Again, maybe you'll tell us more about this, I'm not sure. So to relate to what I was saying before, the analogies with the CMB. So the CMB, the first thing that was detected was just this one number, 3 Kelvin. For pulsar timing arrays, what people are currently looking for is, and setting upper limits on, is the amplitude of some spectrum with some assumed frequency dependence of the stochastic gravitational wave background. So the first thing that will be detected will be some amplitude, and it's not going to really have a strong dependence on the spectrum that you assume, or you won't be able to really disentangle, measure the spectral shape. The second thing will be to try and measure, once this one number is measured, will be to try and measure the shape of the stochastic gravitational wave background. So for example, here you see this green, red, and blue curves are different shapes that are predicted given some assumptions about the populations of supermassive black holes and how they emerge. So this is the equivalent of this FIRAS measuring the blackbody spectrum of the CMB. And this will contain a lot of information about supermassive black holes. The next step will be to try and measure the anisotropies of the stochastic gravitational wave background. Not just measure a sky average number as a function of frequency, but also maybe a background as a function of location on sky. And this has been explored a little bit, but not in great detail. And this is what we've worked on in this paper. And finally, the ultra-futuristic step will be to also, just like for the CMB, look at the polarization of this background. But why not be futuristic? So just, as I said, there's lots of analogies and also some big differences with interferometry. One of the big differences is, I think, best illustrated with a picture like this. So you can arrange your antennas whichever way you want. You can also use the rotation of the Earth to have a complete mapping of the so-called UV plane when you do interferometry. On the other hand, your pulsars are wherever they are. You cannot go and move them. And even if you were to discover a bunch of new pulsars with the SKA or things like this, in order for them to be useful, you will have to be able to time them for, a decade or so. Okay, so the question that one can ask are a bit different here because we have an instrument that is very hard to tune. And so the questions that one can ask in terms of anisotropies, if we don't have a firm prediction of what the anisotropies are, is what is the lamppost that pulsar timing arrays provide? And let's try, lacking some very specific form of the anisotropy, let's try to look under the lamppost. Let's try to find what is the best measured possible anisotropies and whether we can look for this. So this is what hopefully this paper, which has been in the making for like 2 years, will come out in the next month or so. So what we do in a few bullet points, we first derive analytic geometric expressions for the relationship between timing, response, and the stochastic gravitational wave background intensity. I am personally, don't like H plus and H cross and these kind of things. I like having nice tensorial geometric expressions, and they actually make things a lot simpler here. We then derive a simple Fisher matrix in the gravitational wave background map space. So pulsar timing collaborations, of course, do a full Monte Carlo Markov chain Bayesian analysis when they search for a background. But contrary to CMB, where any theorist like me can just make a simple Fisher matrix estimate to see whether something is detectable or not, there wasn't such a simple formalism for PTA, so we've derived something like this. And we've used this to ask the question of what are the principal anisotropies, so the principal maps. We're doing a principal component analysis of pulsar timing arrays. What are the gravitational wave background maps, which are first anisotropic and secondly uncorrelated with the monopole. So these are the maps that we found for the nanograv pulsars. So those maps are not going to tell you much on their own, but the goal will be so that we derive these maps with a simple Fisher matrix. So now these are the anisotropies to which pulsar timing arrays should be the most sensitive in decreasing order. And so the goal would be to provide those to the nanograph collaboration and tell them, hey, once you're bored with the monopole, you can try and look for this anisotropy because this is the most likely form that you might detect. And I will stop here.
Obviously, the most significant anisotropies would come from nearby supermassive black hole binaries, right? And you just need, one of the nearby clusters to have a binary for it to overwhelm the sky, right? So you can't really forecast the existence of such a binary if we don't know it. So the question is, have you tried, I guess, to take the density field of the galaxies and just assume that you have binaries at some fraction of the galaxies, and then the large-scale structure will show up in your map?
So I haven't, because I'm a tourist in this field. But as I said, Chiara Mingarelli has done precisely this. She had some paper where she has taken, I think it was the 2-mass galaxy distribution and have some prescription as to how to populate these galaxies with binaries and some prescription for their separation, etc., and produce some map of where they should be. So if you're interested, you should, yeah, I can put you in contact with her.
Other questions? We look forward to getting the data once they reach the sensitivity.
Yeah, maybe it could be 10 years, but that's why it's a good time to be a theorist and think about what you could do.
Actually, they get now to the level that theorists expected, so it could be next year.
Yeah.
I mean, they were actually hoping to be the first to detect gravitational waves, and then LIGO scooped them.
Right.
Anyway,
Yeah.
Okay. Okay, so I'm going to talk a bit more about supermassive black hole binaries, and mainly on the electromagnetic side, but I will come back to the gravitational wave side in the end. As you probably all know, every massive galaxy has a supermassive black hole in the center, and the central black hole is a very important component of the galaxy, with the mass of the supermassive black hole being correlated with several of the properties of the host galaxy. And here I'm just showing the famous M-sigma relationship with the black hole mass on the y-axis and the velocity dispersion of the bulge on the x-axis. You also probably know that galaxies merge very often to form more massive galaxies. So the natural outcome of this process is that we will have galaxies that will have two supermassive black holes in them. So even though we do observe the first stages of the mergers, and we do see black holes with galaxies with two supermassive black holes, that at kiloparsec separation, it's relatively easy to resolve them with direct imaging, and we have dozens of galaxies identified as dual AGN. As we go to smaller and smaller separations, that becomes more challenging. So here I have the record holding binary at 7 parsec, which is resolved with very long baseline interferometry. But as we go to even smaller separations, that becomes even more challenging, and practically at sub-parsec separation, we cannot resolve them. So we need to find another way to detect supermassive black hole binaries. And of course, at the subparsec separation, these systems are very interesting for several reasons. One, because we don't really understand how these systems get to the subparsec separation. You're probably familiar with the final parsec problem, this idea that binaries may stall at the parsec separation, may never get to the subparsec regime. But they are also very interesting because, as Yacine mentioned, at the final stages, they emit gravitational waves. So how do we go about finding them? One promising method is to look for quasars with periodic variability. And the idea here is that if we have a galaxy merger and there is gas in the galaxies, the gas will end up in the central regions of the galaxies, and it will settle, let's say, in a disk around the black holes. And you've probably heard a lot from Dan and Paul here about these simulations of binaries in a circumbinary disk. So the idea is if you put a binary in a gaseous disk, the binary will act as a propeller. It will expel the gas from the central region, and it will create a cavity of low-dense gas. But the system is much more dynamic than that. As the binary moves around, it pulls streams into the cavity, and the accretion rate onto the black holes is periodic. So that can produce the periodic variability that I'm describing. And here is just the accretion rate onto the two black holes. With green on the top is the smaller black hole, the secondary, and blue is the primary black hole. And then this is just a periodogram of the accretion rate, and you see a peak at the orbital period. So this is one of the ways that binaries can produce periodic variability. A second way is because we have these streams coming into the cavity. There is gas that is bound around its black hole. So if this gas in the mini disks around the black holes is emitting, because the system is moving with a relativistic velocity, even if the luminosity in these black holes, in this gas is constant, we can get periodic variability from relativistic Doppler boost. And the idea is that when the smaller one, which is typically more luminous, is moving towards the observer, it will appear brighter. When it's moving away, it will appear dimmer. So we are lucky to live in a data-rich era. So we have several time domain surveys. And these surveys allowed us to search for this type of periodic variability in quasars now that we have large samples of quasar light curves. So there are of order 150 candidates, some of Matthew Graham's work in the Catalina time domain survey, and some of my work in the Palomar transient factory, and more recently there was another paper on pan-stars that found another candidate. So the occurrence rate in these surveys is about 1/1,000, but I should emphasize that these are only candidates, and this is for several reasons. One, we don't have the baselines to observe many cycles, so we only see a couple of repetitions of the periodicity, and two, the quasar variability is stochastic, which means that it can mimic the periodicity. And of course, we did include the stochastic variability in the analysis, but still we do expect that we have false positives in the samples. So I will just describe a few efforts to identify additional signatures that could increase our confidence in these candidates. And one, I already mentioned how relativistic Doppler boost can produce sinusoidal variability. But an interesting thing with this Doppler boost variability is that the amplitude of the variability depends on the spectral index if we assume that the spectrum is a power law. So if we take the relative amplitude in two different bands, you can see that it depends only on the relative, on the ratio of the spectral indices. And this is a figure from Dan's paper back in the day, after the first detection of a quasar with periodic variability. So Dan took the optical and the UV spectra, and the black is the theoretical prediction. And for the optical, the blue and the red are the predictions for the near UV and far UV. And you can see there are photometric points on this light curve that fit the Doppler boost model, the multi-wavelength prediction. Of course, you can see that the light curve is relatively sparse. So Dan did it for PG1302, and then after all 150 candidates came out, I did it for the entire sample. Of course, you can imagine that it's not easy to get UV data as it is to get optical. So we could do that only for a fraction of the sample. I think it was around 70. And we found that for a significant fraction of them, the optical and UV variability is consistent with this multi-wavelength Doppler boost signature. Of course, we know that also quasars have wavelength-dependent variability, and we decided to do this test, this Doppler boost test for a control sample that is not periodic, so it doesn't have any reason to have this Doppler boost signature. And we saw that by chance it happens for a fraction of quasars. So this is not a clear signature, but there are two things that you should get out of this table. One, that the Doppler boost signature happens more often for the sample of candidates, so maybe there are some interesting sources. And two, when we go from the far UV to the near UV, which means when we go from worse data to better quality data, the chance coincidence decreases. So maybe with better data, we will be able to distinguish the signature much better. So motivated by this, we wrote a few proposals to Swift to follow up PG1302, which is the first source that I mentioned. And we got about 10 data points in a couple of years. And this is a follow-up to the model I was describing that Dan came up with. And the blue is the prediction of the model, both in optical and UV. And these are the new data that we got with Swift. So I had a student work on that, and we found that our new observations are still consistent with the Doppler boost model. But of course, still, even though we have more data points now, the light curve is sparse, and it's better if we have more data. Of course, Cheng did the full statistical analysis, and you can find it in the paper. Another potential signature, again, it has to do with these mini disks formed around its black hole. Oh, okay. And the idea is that if the mini disks are able to produce broad emission lines, then the motion of the mini disks will be imprinted on the broad lines in the spectrum. So we went back to Palomar and took spectra from all the candidates. And interestingly, some of them do seem to have variability. So of course, maybe that means nothing, but if we go back and take more spectra and see these coherent changes in the spectral lines, maybe that will be something. I meant to talk about gravitational waves, but I'll just say only in one slide that, of course, we haven't found anything yet. But when you don't find something, you just put upper limits. And given the upper limits on individual supermassive black holes, that's not on the background, we can put upper limits on tentative binaries on individual galaxies. So I did this project for Nanograph that I compiled the galaxy catalog in the local universe. We found all the massive galaxies that are within the volume that Nanograph can probe. And then we started placing constraints on the chirp mass of hypothetical binaries these galaxies could host. And if we know the total mass of the galaxy, then we can place constraints on the mass ratio of these binaries. And I will just leave you with the graphic summary up here. And if anyone wants to talk more about this, I'll be here tomorrow. Thank you.
pressure or the fact that these jets as a form of barriers would would tend to separate them or just make it less likely they would have these runoff flows.
So you're thinking that the jets would affect the disk, or?
Well, I think that there should be some large-scale interaction hydrodynamically between the pressures that are being generated by strong outflows, so it might be less likely that closely associated binaries would be jetted.
Well, you probably have to ask the theorists here. They know more about that.
Also, jets are ubiquitous only in 10% of our quasars, so perhaps.
Yeah, two of them is almost exactly.
Yeah, actually, it was not discussed in the paper. It's a good work. Any other questions? Well, if not, happy holidays to everyone. See you at the end of January.